back to the MLIR Open Design meeting. Today we actually have a sort of design meeting where we want to look at generalizing the Verif dialect from circuits to more of software concepts that are prevalent in MLIR. And I think Max is going to drive this. So if it's the case, Max, the screen is yours.
Let me share screen. Okay, so I posted a link in the chat, pasted a link in the chat. If you didn't see that, you can go to this address, which is my name, GitHub.io, and then click the last link. Or just click the link in chat. Okay. So this is a slide. This is not a slide deck. This is a collab. You can follow along if you want. It's not super important that you do. You're not going to get much out of it. If like this is usable use, but it's not useful. It's running code that's a sketch that serves just as a prop to center our discussion on concrete things. Okay, so let's ignore. So you install this package, blah, blah. You make some imports. None of that is important. Boilerplate. Okay, so the context of the prop for today's discussion, and this is just one of a bunch of examples people can think of. Of course, after I finish speaking, however long I speak, 25 minutes, whatever, feel free to suggest other examples. This is just one example that I cooked up. It's actually in the RFC, or it's mentioned in the RFC. We have a kernel in some kernel language. It happens to be Triton, and you want to verify the ranges of some parameters so that you can avail yourself of some optimization opportunity. The particular optimization opportunity I mentioned in the RFC is this thing called buffer ops on AMD GPUs. If you can get base pointers and offset strides, blah, 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 arranged to be in a certain way, then you can take advantage of buffer op instructions, which are in-memory arithmetic kinds of instructions. And the kernel lang that I happen to work on during my day job is Triton. So this is the kernel that I'm going to display here is Triton, blah, blah. Okay. So the kernel is a standard kernel. If anybody, it just not really matter for the discussion or SMT or Verif, but so this is Triton. And this looks 99% like Triton. So if you click to this example, which is in Triton, you will see basically all the same exact stuff, of course, except for Verif. But this is not Triton. This is the Python bindings for the Triton dialect, blah, blah, blah. Again, not super important, but just don't be surprised if you try to write this in actual Triton and it doesn't do anything because it won't work. Okay. So the kernel is a matmul kernel. It's a standard matmul kernel. I guess it's blocked. It's blocked. It's not the most naive implementation of matmul. It's a blocked matmul. And in order to write a blocked matmul in Triton, you got to do all of this PID indexing offset arithmetic. Again, not super important that you understand how Triton works if you're not familiar with Triton. The only thing that you take away from these lines and these lines is that there's a bunch of arithmetic on some runtime provided values, essentially. So there are two runtime, there's a bunch of runtime provided values here, the strides, the dimensions of the matrix. The two that are most important, or at least that I'm going to verify properties of, or verify properties downstream of, are what's called the PID program ID and one of the characteristic dimensions of the matmul. So the PID in Triton is this thing like thread index or worker ID or something. Doesn't really matter, but it uniquely identifies the worker in a block and grid of workers. According to this PID, you select which data you want to operate on. And so if you want, if you want to construct a pointer, so what this ends up being is a pointer offset into your data that's a function of your unique ID. And if for the buffer ops to work, two things have to be true. For the buffer ops to be available, two things have to be true. The base pointer has to be 32 bits, not 64 bits, which is not that hard. That's a platform constraint, really. So all the pointers will always be actually 32 bits, so coming into the kernel. But you could push them out of bounds, right, by doing all of this weird arithmetic where I multiply, blah, 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 divide, multiply, add. You could push the PID beyond 32 bits. It's not impossible. So that's one thing that needs to be verified. The other thing that needs to be verified is there are these offset tensors. Again, if you don't know that Triton works on blocks of data, is a block programming model. Just imagine this is a scalar offset. And so for buffer ops to be available, you need offsets to be non-negative. Scalar offset, tensor offset, whatever, tensor of offsets, whatever, doesn't matter. These things need to be non-negative. So these two properties need to be verified. And I want to say, and I mentioned this in the RFC, we have an implementation of this, right? So like you go to Triton, you run it on AMD, this works. That's not a advertisement for AMD. I'm just saying that there are alternative ways to do this using just existing upstream infrastructure. So two ways to do this are like affine value bounds op interface or value op bounds interface, whatever. And that's the first one. And the other one is integer range analysis. And so we downstream use integer range analysis. I built out an integer range analysis thing for verifying not the 32-bit width. I said that's a platform known entity. So we're just leaving that aside. And but we are verifying non-negativity, and we're doing it using integer range analysis using data flow analysis, which is built on top of data flow analysis. So this is possible. You don't need, you can solve a lot of like simple problems, or you can solve some set of problems using built upstream infra, whatever people have thought about, considered, deemed worthy of build out upstream or deemed necessary. The solution works, but it's not great, which is why I was thinking about SMT and then eventually like put together this RFC. One of the things that is, so in Triton, you can write these things TL.assume, yeah, right? So the LLM here predicts this because this is a common Triton kernel thing. If you go to look at Triton kernels, sometimes they will have this. This is actually a trick. What this operation in Triton really is LLVM assume. And LLVM assume, I mentioned this last time, is not about assumptions. It's about really, I believe, branch prediction. So if you've ever seen in C++ code, like in LLVM, we have these macros called LLVM likely or unlikely. They are hints to the compiler and the branch predictor to elide branches in conditionals. They're being abused. So this LLVM assume thing is being abused in Triton or overloaded to implement assumptions. And it's used in a couple of different ways. One of the ways that these assumptions are used in Triton are for what I mentioned. Hey, I'm going to let the kernel author write a bunch of like assumptions like this, which are inequalities, and then I'm going to try to combine them. So one of the defects of the current implementation, which only has available upstream infra, is you can't actually do this. So this thing, let's say I wanted to do this, or if so this fails not because the syntax is incorrect. This fails because this is effectively two assumptions on one symbolic. And upstream integer range analysis, because what's the way to put this? It's conservative, or I don't know, whatever. You can't essentially like you can't do intersections because every update from the data flow analysis has to converge, i.e. get bigger. If you had intersections, you could get like cyclical states in the data flow analysis engine. So you can't combine assumptions. We have some hack arounds for this because sometimes we do need this. But this is, of course, two assumptions that could be so upstream integer range analysis can't do this. I believe affine analysis could do this because, again, affine analysis is basically like some SMT theory anyway. It's a kind of like more robust implementation of that SMT theory. So does enable you to combine assumptions in some such way. But the most straightforward thing is, hey, I want an SMT, a query that has two assumptions, PID greater than 0, PID less than 10, and then let the solver itself, the SMT solver, figure out how to combine them in its backtracking, whatever. Okay, so that's a whole bunch of words giving context. I'm going to summarize the context. The context is, I have this set of arithmetic. I want to so because the Verif and SMT infrastructure is not fully built out, I did not, this might actually work right out of the box, but I didn't check whether all of this stuff would work with array types. So there are array types in SMT dialect. I believe it'll work. These are tensors, right? In Triton land, these are tensors. They're whatever, tensors of TT pointer or tensors of I32 or whatever. And maybe I could do all of the same stuff that I'm doing on these values, but I'm just simplifying and saying, I want to prove that these things are greater than 1 or greater than 0, non-negative, right? Because these PIDM and PIDN actually inform, after some more arithmetic, what the offsets will be, and I'm checking non-negativity. So the property that I want to verify is non-negativity of these offsets, i.e. non-negativity of these things. So I can change this to 0, it doesn't matter. I'm going to leave it so it doesn't break. But again, non-negativity is what I'm trying to verify. Okay. In the standard kernel, and I could pull it up, this arithmetic is just, it's here. It's just right here, right? There's no verif contract, there's no region op, there's no annotation, nothing. Because again, currently Triton has no knowledge of SMT. In my rewritten and how I imagine slightly, right? Like squint and imagine the built-in unrealized casts missing, and then some of the unnecessary bracing and parentheses and stuff like missing, and right, like this is hastily sketched together after work last night. Somebody would write something like this: verif.contract, and in fact, there would be no for all. The for all is a hack. There should actually, right, like kind of the argument that I made last time was verif is going to be the UX around SMT. And so these asserts, which are actually ensures and requires in verif, something like that. So there would be no SMT that the user themselves would need to write, although if they choose to, they can, right? But ideally, right, you have verif, contract, and inside there are some assumptions about what the significance of the operations in the verif contract are, and the SMT is added and sprinkled and lowered therefrom. Okay, but again, this is incomplete infrastructure. This is a working implementation, but it is an incomplete implementation. So I have to write SMT assert, and I also have to write for all. I'll come back to this in a second. But the point is, I'm going to annotate the standard computation with something like verif.contract. And in one flow, the dressing and annotation disappears, and the kernel just compiles and runs like the standard kernel. And in another flow, the verification flow, something else happens. Let's see what happens. Okay, so what I'm going to do is I'm going to print the MLIR associated with this kernel. Yeah, fuck. What broke? Oh, because I reran the, yeah, okay, sorry. Let me restart because this is storing global symbols. So I want to restart session run. Okay. Sorry, it's gonna take a little bit to install. So just repeating what I said, there's nothing broken with the example. What happens is I have a global module. I should have just renamed the kernel name, but didn't think. I have a global context and a global module, and this little bit of magic emits the same kernel twice, and there was a collision. That's what the error was about. Okay, so this is the kernel. It's printed, a whole bunch of Triton dialect, arith dialect. It's right. It's primarily Triton and arith. Triton famously doesn't use anything from upstream except for like SCF and arith, and yeah, that's it. Okay, so this is the kernel. There's a whole bunch of stuff. If you're not familiar with reading this stuff, it's not super intelligible. The kind of important thing, I don't know what's important, but the fact that like Verif contract is emitted, I don't know. Maybe there's nothing to take away from this other than this is legal currently, which also doesn't mean anything because I just hastily sketched together. Okay, so there's a Verif contract. We saw it up top. There's a for all, blah, blah, blah. There's a yield. And as I was saying, can I make this bigger? No. As I was saying, in one flow, all of this will just disappear. And what will remain is just the stuff, all of the arith comparison, division, blah, 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 that was there, would be there, were we not to annotate it all. Okay. So that works, and you can run the program, blah, blah, blah. You can, again, this is like opt-in. I guess basically the whole point is that it's opt-in. What I sketched out and what the rest of the collab will show and demonstrate is kind of, so this is what I ended up learning was there are ways in which Verif from circuit doesn't really work for us. There's some assumptions or like their flows, like like the lowering paths that they currently have, they're like 95% usable upstream. But the particular thing that I wanted that kind of works but kind of doesn't is I wanted the contract to pop out into its own region, module, whatever. And I wanted to just play with the contract, lower it to SMT, export to SMT-lib, verify, run it through a solver, right? And that kind of works, but the way that they prefer to do this is by, they inline the verif into a verif formal, the verif contract into a verif formal. The verif formal is typically inside one of their hardware modules. Symbolic values in the contract itself, like the characteristic parameter n, turn into verif symbolic values that then become parameters on the hardware module, right? Because circuit is all about RTL, ASIC, or whatever, and they have input-output ports on their modules, and they verify at the module boundary, right? So Verif is set up to do this. So I had to hack a bunch of stuff to make this work without hardware module and without hardware module parameters, which would not fit upstream. Okay, but so what did I hack and what comes out? Okay, so it kind of comes out. So lower the contract, and you get what I said, kind of. You get a module. So this pops out, and I skipped a step actually. So this pops out into a Verif formal, and then the SMT, and then directly into an SMT solver region. I actually don't know why I don't know why I did something here, but it's supposed to go into the Verif formal first. It doesn't really matter. So you get two things. You get the operations cloned, duplicated, right? Except for the SMT for all. If there were no SMT for all, and as I said in the beginning, the SMT for all should actually be encapsulated in Verif, right? I want to verify some properties about my IR for all possible values of an input parameter, like a function parameter. That should be encapsulated in Verif. And so the user would never write SMT for all. And so the SMT for all would not be in the final module. What would be is in the final module are just the original statements, right? And the SMT asserts wouldn't be there. So this kind of worked. This kind of works, or kind of resembles what a future flow or path might look like, right? The original operations remain in the module, undisturbed, basically. And you also get a separate region, module, whatever, that you can verify that reflects. This must have happened twice. Yeah, the reason this failed is must have happened twice or something like that, because the lower contract is not supposed to translate to SMT. So there are two passes that were applied here. The contract was pulled out into a Verif formal, and then also the arith was translated to directly SMT, and then some canonicalization, right? So if you look at these operations, arith add I, blah, blah, arg4, arith sub I, division, sign division, multiplication, remainder sign, blah, blah. You have the corresponding SMT operations, which are basically spelled the same way, kind of. And this is so here, after a whole bunch of hacking, there's nothing that can't be directly translated to SMT. So again, as I said, for some reason, both of these steps got applied. I don't know why, but if you run the Colab step by step, what you will see is a Verif formal, and then inside the Verif formal, you will see arith, and then after this pass, which converts the arith to SMT, you will see what is visible here. Don't know why this happened. What happens here? Yeah, so we're going to get the same thing as it's a no-op. Okay, and here this is kind of the end state just prior to egress. There's some discussion to be had about here vis-a-vis how circuit currently verifies this, it connects it to a solver. This was mentioned briefly last time. The way that they do this is lowered to LLVMIR function calls or API calls on Z3 that instantiate these operations. So, right, like Z3 has some API, Z3 create bit vector sign division on some object, right? You could do that. They have their reasons for doing this, but the alternative for connecting this to a solver is, hey, let's just translate everything in the body to SMT-lib. I'm going to skip this. We can come back to this. So that's what's happening here, right? So I have everything here is legal SMT dialect. Took some work to get it that way up here. Translate, export to SMT-lib. This is no longer MLIR in the slightest. This is an SMT-lib query that asserts that PID is greater than 1. And then for all n tries to assert this, right? That's how to read this. And then there's an instruction to the SMT solver to check for satisfaction. You can also request satisfying the values, right? You can request an instance or whatever it's called. I did not do that. That's typically, at least for this use case, it's not important. For other use cases, it might be important. Like, for example, you're searching for a kernel that satisfies some properties. You're searching. This is just verification. Yeah, okay. So this is SMT-lib, and Z3 will parse this happily. And this ran, Colab says there's a check. So import Z3, stand up, turn on the solver, instantiate the solver, create the query from a string, and then run check, and then see whether you get the satisfiable answer. And there's an assert, and it passed, so that means it was satisfiable. Okay, summarize before we dive deep into certain things. Okay, so we started with a matmul kernel that had some arithmetic that needed to be verified, non-negativity, blah, blah, blah. Hand annotated, minimal annotation is the goal, right? Add some assumptions about some key SSA values or properties or whatever you want to think of it as. Lower in such a way where the original kernel remains intact and still usable. So that's this, where, as I said, this would disappear in the far future or in the beautiful future. Lower to the reusable kernel, fully usable kernel, and a verifiable program. Lower the verifiable program all the way to SMT-lib. run the SMT lib through your solver of choice. It doesn't have to be C3, right? CVC5 is another one. There are other niche solvers that do such and such things better or better suited for such and such programs. Yeah, that's it. So that's the flow I envision, or one such flow. That it's not the most generic. I don't know if it's the most common. I feel like it would kind of be common because oftentimes you want to verify things about your kernels. This is not translation validation, by the way, verification or validation, whatever it is, which is what Circuit heavily focuses on currently by in its LEC tools, logical equivalence checking tools. It's also so translation validation is also what Alive 2 does. That's not what this is. That's not the same flow. There would need to be more discussion. So, right, this is one flow. Here's how it looked like. A high-level comment. After putting this together last night and running into some dead ends and some problems, I basically came to the conclusion that there's less to be salvaged than I would have hoped for, particularly because the passes themselves in currently in Circuit like inline into specific hardware specific hardware module, whatever. They take these regions, these Verif contract regions, and they inline them somewhere. What do they inline them into? They inline them into a hardware module. We're not upstreaming a hardware module. I just want to inline that region into a module or the module or something like that. And I'm not gonna. I don't know. I don't think it's really worth it disturbing those existing flows or generalizing those existing flows. Maybe it is. We can talk about that. The takeaway here is I think we probably are well suited or better suited just to redesign this upstream ourselves, taking inspiration. Like basically, we or I have to do some thinking that I was trying to avoid, kind of like ride the coattails of Circuit, whatever. Okay, so that's the summary. It kind of works. It could kind of work if you twist your head, contort yourself, contort the bunch of things. This is one way that it could be used. Other flows, like translation validation, need some more thinking. This is why I said the same thing. The other thing, like if we want to support more than just verification, we need to think more about what I've described here. Like what I've described here does not necessarily, because there's no comparison between input-output values, captured or represented or anything like that here. So effectively, we need to do more thinking, designing Verif upstream to support this and translation validation and like search. Like 3 use cases I think that are going to be useful or are useful are I want to verify subsets of my program. I want to verify, validate translations, transformations, and I want to search something. I want to use the solver in a search verify loop. And so those 3 use cases, the latter, which is not at all considered by Circuit, I don't think, needs more than this. I'm just demoing the first one. Hey, verifying a subset, but there are more examples. Okay, I don't know. This isn't really interesting, useful to talk about the kind of like, I'm rewriting a bunch of stuff in Python because I was too lazy to write it in C++. These are like the hacks to make what I have currently work without hardware module. Okay, I'm going to stop talking, open up the floor for questions. We can jump to any part of the thing, blah, blah.
Hey, this is Houston Haynes. Can I jump in?
Sure, of course.
So I'm brand new to this area, but have been looking at my code of choice is F sharp and looking at F star, which has its own little ecosystem of going to SMT lib.
Yeah.
And one of the things I was considering was actually doing all of the verification upstream and then simply taking the assets or the output of the verification and preserving it through the lowering process, as opposed to actually doing it during lowering. And I'm just debating with myself, and you seem to be right in the same area. So I'm kind of curious about, have you given any consideration to that So that I'm just
So
doing
what-
it in its own stack and then just moving it through the lowering process.
You mean verifying in the front end? I guess
Yeah.
you're basically saying writing upstream of MLIR and F#. Yeah, that's
Well,
sorry, go ahead.
F# has a annotation mechanism because F* is based on F#, or at least partly. It's one of the parents of F*.
So,
You can
sorry,
actually just put F# annotations that then kicks off, all the algorithms in F* to be able to do the calculation. So it's a way of having them closely coupled.
Sorry, so I can annotate just F# with F* verification?
Yes, that's correct.
Okay, sure, that makes sense. But the relationship to MLIR is you're envisioning writing MLIR kernels or MLIR programs in F#, which has been annotated with F*.
That's correct. And going through MLIR and LLVM to create binaries as opposed to and completely bypassing the .NET ecosystem.
Yeah, that's certainly one approach. Anybody can speak to this better than I can, but so this enables you to do the first thing. This enables you to do what I've shown, which is I want to verify some small or whole functions or bound whatever F# and F* enable you to do, right? It does not enable you to unless F#, I'm not aware that it does, has a macro system, you can't rewrite F# programs. So you can't do translation validation in F# using F* with F* verifying the rewrites of the F# kernel. Again, unless F# has a macro system that I'm not aware of, it might. F* might, I don't know. But the point is, right, like MLIR is a term rewriter. And so if most front ends aren't, most front ends aren't Lisp, most front ends don't have macro systems. Some of them do, whatever. And you can do verification at the front end, right? Like Rust has a robust macro system, and I could see doing verification, translation validation, and search all in Rust in Rust, because you can use macros in Rust to rewrite the AST of your kernel. Okay, that's plausible. But if your language doesn't have it, and again, I don't think F# does, you can verify, and then you can lower to LLVM or whatever through MLIR, but you're not going to be able to do translation validation. You're going to be able to do and you're not going to be able to do search, which is an important kind of, at least search where the AST is changing. Certainly, there are people. So one project team in my org, blah blah. A lot of people do this. It was mentioned last time by Suraj. Hey, I'm gonna search the kernel space along some dimensions. This is kind of like the boon of structured programming. Again, like anybody, there's a bunch of people that are decades of experience in this, right? You rewrite the kernel because the transformations are parameterized. So like linalg and the whole structured code gen thing in MLIRs, I'm going to do lowerings, but they're parameterized. I'm going to tile, I'm going to vectorize, whatever, according to some parameters. Okay, so that induces a bunch of transformations. And each of those transformations you potentially want to verify. Now, because they're structured, you know a priori, because if you assume the programmers did a good job that implemented the passes in MLIR, you're not going to generate invalid kernels. But whatever, you might be working on your own, and you want to verify those. And that's something you can't do using what you described, but you can do a limited subset of this at the front end. You can let the solver live independently of your kernel emission infrastructure. So you can be like, I'm going to generate a bunch of matmols in Python, and they're going to have a bunch of parameters. And for each one of them, I'm going to run the solver somehow. People do this. This is a way to do search, the third arm. Not, again, this isn't translation validation. You still have to rely on the implementer to be correct and a good programmer. But search. Okay, anyway, there's a lot of words to say. You can skip this, yes.
That's interesting. Thank you for filling me in on that. That's part of I think the landscape that I really haven't traversed yet.
Cool.
Another point is that if you have the proofs in the same level as the IR of the program, you can do better optimization. And that is the case on Ada Spark, where a Spark program that is proved can run faster with the proof.
Yeah, this is the search kind of
Yes.
use case.
So you can use the assumptions and asserts as optimization hints.
Yeah. Yeah. Yeah.
That's really helpful. Thank you.
Alex, any comments?
And the overall flow makes sense to me. I guess we can spend time looking at individual operations and how we think they can be ported.
You mean literally ops? Oh, sorry,
Yeah,
you mean
literally ops.
you mean Verif ops?
Yeah, I mean Verif ops, like, because you mentioned you did some hacks, so
Yeah.
unless there are some other high level questions, we can go to a lower level and look at hacks and try to be productive and figure out a way how to just start introducing them.
Sure.
Unless there are better ideas from the audience.
Yeah, just one thing I want to mention. So there's like one other use case I've been like doing quite a lot recently is like I've been using the SMT. So it's kind of the same SMT dialect. So you mentioned translation validation. So I've been using it to like try to find bugs a bit in MLIR. But I also used it to like prove that some rewrites are correct. So if you have like a PDL pattern, have like a lowering from PDL to SMT to check if it's correct for like all inputs. And I've been trying to use it a bit to try to prove like canonicalization patterns in Arif. So it's kind of also one use case, I guess, on the SMT dialect. It's just like trying to prove a bit more, yeah, like trying to prove rewrite / fuzzing in general to just like make MLIR a bit more correct.
This is interesting. You're proving the correctness of a PDL program.
Yes.
What do you lower? What? So can you? Because this is meta. Can you give
There's
me
something a bit meta is for that you need to represent your rewrites from. So let's say you go from Arif add to SMT. You need to represent this exact thing in a bit a more. So for anything that doesn't have attributes, that just works. You can just like in your PDL lowering, you call a different lowering to just lower the Arif that is inside it. So there's a bit of meta things going on, but it kind of it just works.
Are you proving? Sorry, are you proving the PDL program, or are you? I said that, and I wanted to be.
Yeah, so you're proving that the PDL, like the rewrite pattern, defined as PDL, is correct for all inputs.
Okay.
So that way, instead of just saying this program was compiled correctly, you say any program that uses this rewrite pattern, well, you know that whenever the rewrite pattern is applied, it's going to be correct.
Sure. I'm lost on I get lost in the relationship to a RIF without attributes.
Oh, so if you have a PDL pattern that says match an Arif operation and just like create new Arif operation, as long as these Arif operations don't have attributes, it's really easy to write this lowering in some sense. When there's attributes, they're just like more complex things going on, and defining this lowering is a bit kind of complex.
Is that and are you saying that that's where the verification comes in? That's the
No, that's just like okay. Maybe I should take a step back. So now, the semantics of Arif is defined as a translation from Arif to SMT, right?
In your world, but sure, yeah.
Yeah, okay. So it's like the lowering from Arif to SMT is essentially just saying, oh, this is the semantics of my particular operation. The thing is, in PDL, you need to say something like, what is the semantics of this arif operation for all possible attributes that can go on it. Let's say all the possible overflow flags.
Mhm.
And in that case, just using a simple lowering from arif to SMT doesn't really work because you need to be like, oh, it needs to be valid for all different kind of attributes.
You're doing, I guess you're doing like, so I think I got what you're saying, because the semantics of arith, you're basically checking whether the semantics of the, like I have a program just of arith.
Yeah.
And the semantics are quote unquote, you're doing proof checking by like equivalence, or I mean logical equivalence checking, I guess. You lower before and after the PDL rewrite and see whether the SMT lib are equivalent. Is that correct?
Exactly, yeah.
Yeah,
It's
okay.
technically not equivalence, but it's the same thing. Yeah.
Yeah, gotcha. Okay, cool. Yeah, that's an interesting one. Proving
So
the
that's
PDL rewrites. Yeah.
Yeah, so that's a fun use case. One more thing is that we have a different lowering to arif. So your lowering to arif goes, I mean, you don't handle poison from what I understand, right?
No, yeah.
Yeah, so
Nobody should take anything seriously. I just did a regex like of the comm to SMT. Yeah.
So we have a more complex lowering. So like technically each I32 is lowered to an I32 I1 where you have like this I1 representing is it poison or not.
Yeah, Martin mentioned this last time. Yeah.
So I think your thing, yeah, I mean, your thing will work as long as there's no poison. So that's like for your use case, I think it's completely fine. But for the use case of like, I think.
Well, so what's funny is that I have gotten kernels from Triton, in fact, somewhere, somehow, that have had poison in them.
Oh, okay.
Yeah. Anyway, the arith lowering to SMT is neither here nor there. Like a better job before that is upstreamed will absolutely, like I was always intending on revisiting and doing the actually like scientist correct thing there. Yeah. Yeah, cool. Okay, Alex, you want to dive in? Okay. Sorry, before we dive in, does anybody have any more like high level questions?
I can actually suggest, since there seems to be enough interest in using that, and we have like 14 minutes left in this call, we'll clearly not do the entire design, but maybe folks interested in using this, you can band up together into a sort of a working group and get a higher bandwidth discussion if it's helpful. Just suggesting we have one on tensor compiler, we might as well have one on verification.
That sounds like a lot of work.
It is, but think about it, and we can, like, you don't have to have it. Just if you want more.
Go ahead, sorry.
Yeah, if you want more hands on deck, or if you want feedback from use cases other than yours early, before we go through whatever RFC or code review process, where somebody comes and says, oh, I have this use case where I verify PDL and it doesn't fully match my use case, so can you design it differently? I feel like getting that earlier is beneficial.
Yeah, I agree. Yeah, I wasn't, yeah, so I'm not opposed to having as many people contribute at the forefront so we avoid exactly this problem where we code ourselves into a corner. I just wasn't sure whether this was going to be that serious. Yeah, I mean, it's fine. I'm saying nonsense. Yeah, so we should start a working group and take it seriously.
Yeah, we can do by having people self-select. Let's do a dry run. Start one, see who shows up, and see how much effort they're willing to put in.
Sure.
At least that will give you an idea of how many people you can rely on.
Sure.
Yeah, also one point is that I think we probably all agree on the SMT dialect thing.
Yeah.
I think it's just the verif part where people might have opinions, but I think the SMT thing seems pretty non-controversial because it's just, I mean, it's a one-to-one mapping from SMT lib to this.
Yeah.
So there's also
I think on SMT we pretty much concluded that it was fine, and I haven't seen any concerns in the forum since the last time. So at this point, let's just start code review and approvals.
Yeah, there's no reason we can't start SMT. Did that reshare? Yeah, that reshared. Yeah, I'm gonna ping people on the PRs. I was planning on pinging people on the PRs today to remind them to start reviewing. So is the decision is like punt the discussion on the hacky rewrites to the working group, or Alex, you want to ask some?
I mean, we have 10 minutes. If there is something we can do in 10 minutes, let's do that. If not, let's just give people time back.
Oh, sure. Yeah, that's fine too.
And we can also do it like, let's start, and if people are not interested in hacks, thank you for coming, and see you next time. I think we have something planned.
Yeah, we have a talk on interaction. Is that the next one?
Oh yes, so somebody on the chat
Hopefully.
says if they can quickly introduce themselves. Yes, please do.
Yes. Hey, go ahead.
Hey, how are you? My name is Martin.
Good. How are you, man?
Good evening, everyone. I proposed the interaction combinators next meeting. So I just wanted to introduce myself. I'm working I'm working by myself. I contribute open source. I'm not affiliated with any company. I do go to college. And I've been studying graphical calculus for a few years now, and I would like to contribute this dialect because I've seen so far at least 2 languages and 2 VMs for interaction combinators, and I think they're already like mature and simple enough to work with in this graph rewriting framework of MLIR. I have a prototype which works pretty well, but I would like to know what everyone sees in this effort. And maybe like I'm talking with one of these languages, which is Vine, and they have their own compiler as well. So I will try to use their front end with this interaction net dialect as a backend. I'm not trying to add any syntax or anything like that. Just the backend part and the rewriting. So yeah, I just posted some potential agenda in the MLIR. Well, it's a thread in the MLIR. Maybe you can see it. Anyway, thanks. Yeah, that's me.
Yeah,
Thanks for
welcome.
listening.
I suppose as like a quick comment, so you know what to expect. I think the main decision point, or main decision criterion we have for dialects is there a community willing to maintain, like first develop and maintain and support the dialect over time? Because overall the economics of sorts that you have in a project is when there is a dialect that's being added to upstream, it means whoever are current upstream maintainers get more work. And well, you are in a similar case where many of us do it outside of our paid work. So like, I do it as a volunteer. It's my sort of hobby. I do it on weekends, I do it on evenings, or whatever, whenever I can. So it's a trade-off of how much extra work the community, the existing community of MLIR will get versus how many new members we can bring into the community that will do support work. So if you can maybe a bit think in those terms and think like, okay, you mentioned there are 2 languages that use this. Can we somehow attract people from those languages to also become contributors or maintainers, not maintainers in a sense like project maintainers, but somebody who would come and eventually fix bugs and update documentation and do usual software plumbing. That's and that's also true for SMT and Verif. It's just that the discussion shows that we have enough people who express support, and I would feel justified saying, "Hey, Mathieu, you express support for this. How about you come and fix these bugs?" sorry, Matthew, for picking your name and putting you on the spot, but you seem to be really interested. But that's the kind of dynamics we are looking for.
Okay, I will definitely consider that and write down some of my thoughts. I will try to get some Vine developers in the design meeting as well. I'm familiar with them, and I'm in fact trying to develop this dialect so that they can use MLIR. Maybe consider using MLIR instead of writing a whole new compiler, because I see they have a lot of issues. Like everyone has their new numeric types, for example, and everything is starting from scratch. And this dialect seems very natural fit for MLIR. I guess they will be very interested, but I still, yeah, hopefully.
Yeah, it's an interesting, like community building is an interesting problem. We should definitely discuss more details, and then we can see where we can take your proposal from there.
Sounds good.
Okay, I think at this point there's like 6 minutes left, so sorry, Max, for a bit hijacking this, but we are probably not going to discuss details. We can synchronize offline on Discord or wherever and see like what's actually the best format to proceed. Do you want to go and just make a first draft and have people react to that? Do we want to, do we need a call actually, or can we just, I don't know, throw draft PRs around and see sure sums up, or here's my change on top of that might be faster? Like I'm not saying I have to be particularly involved in that. I just have some experience with upstream design, but basically trying to
I'd
select
appreciate your
more
help.
people.
I'd appreciate your help because I've actually never done this thing where I design a dialect. Yeah, it's funny. A lot of people start with that. I did not start with that, so I definitely appreciate your help to the extent that you have time.
Yeah.
Let's do this offline. I think Discord is fine.
Sure.
Okay.
Well, thank you everyone again, and thank you for Mike. Sorry, what's her name again? Leventhal?
Max. Just call me Max.
Sorry, and thank you for lending me some of your time.
No, 100%.
Sure, no worries. Okay, I think we can conclude here unless there are some last minute points.
Thanks for letting me jump in too.
No.
Sure, of course. That's the point. It's like I guess I have a concluding remark that we, as in the MLIR area team, are trying to bring back ODM. We haven't had one for the last year. And we are also trying to reframe it into more of a design meeting, as the name implies, open design meeting, where we discuss designs, because in the end, it started being a sort of research seminar where people come and present work that has been done. While it's certainly interesting, it is rarely actionable. Like we can say, oh, you could have designed it the other way around, but if somebody already spent a year or two doing the design, they're not going to revise it. So just a general encouragement, if you are thinking about some problems where you would use MLIR, design a new dialect, design a new path, break the notion of path pipelines, break the notion of dialects, whatever, any crazy idea, please bring it in. And the point is to really start leveraging the common knowledge we share on the different aspects we have in MLIR, in LLVM, and compilers in general. We want to be more open than we have historically been towards discussing ideas, not necessarily going as to, okay, we discussed, let's implement it right now, but to learn something and build on that over time.
That's really great. I'm very much in the learning phase, and I feel like I'm kind of starting from square one, but I appreciate everyone's input and helping me get ramped up quickly.
Awesome. On that note, I think we can conclude. Thanks everyone for coming, and see you next week.
Yes.
Cheers.